All right, welcome back. So we're going to go ahead and look at some MAF signals and how to do some probing on this car. This, of course, my Trans Am. And we can see right off the bat that we have a lot of homology with what we just learned. So zooming in, we can see what is clearly an intake air temperature sensor. This is the MAF sensor. This is actually an aftermarket MAF with a larger diameter to match the larger diameter intake manifold, as some modifications I did. And we'll talk a little bit about performance with these things in the third part of this series. But let's go ahead and take a closer look at the wiring on this MAF. And we can see from the wiring on this MAF there are 3 wires. So without needing a wiring diagram, without having to consult a manual, without having to rely on some fancy Varus or whatever that would cheat and tell you what these wires are, we should be able to pretty easily figure out what these wires are very quickly, because we now understand the operation of this sensor. And incidentally, these are this is an aftermarket pattern. If we look here, this is the original harness connector, and we can see we've got a red, a black, and a yellow. And again, I do not know. I've actually never done this before, but I am going to guess, as I hope you would, that the red wire is probably going to be the 12-volt power, the black wire probably ground, and the yellow wire probably a 5-volt reference, wouldn't you think? So let's just go ahead and, before we break out a scan tool or anything like that, let's just go ahead and verify that. All right, real quick disclaimer: as a result of all the idiots that have fried their PCMs trying to do this when they didn't understand the material, this is definitely one of those cases where if you don't know what you're doing, you can destroy the PCM, especially because we're dealing with a 12-volt source here. If you send that 12-volt source directly to the ground, then pretty much either way you look at it, if that 12-volt source is coming from the PCM and you put it directly to the ground without the wire, the MAF wire in between, you're going to fry that PCM. Conversely, if the ground is controlled by the computer and the computer is grounding it, and you put the 12-volt by accident right to that ground, you're going to destroy that computer. So a lot of people have asked me to do a video on how to not blow up your computer. There is no such thing. Understanding the circuit design and understanding the PCM control is integral to knowing how to not fry your PCM here. So I just wanted to make that comment. Don't do this unless you're comfortable with what you're doing. All right, I'm pretty sure I won't need the engine running for this, which is nice because the engine's kind of loud. I'm pretty sure just ignition on will have a 5-volt and even a 12-volt to the MAF at all times here. So what I'm going to do, let's just disconnect this and first of all see if we were correct on our wiring guesses. I am quite positive that the black is going to be the ground, so I'm going to carefully go ahead and probe the red wire, and there we see our 12 volts, obviously. So that is the power wire, of course, for the MAF wire itself. That means this other one's going to be 5-volt reference there, and we can see 5 volts. So actually, we even did a little troubleshooting here, even though we didn't mean to. We have verified without question that we have ground, signal, and power at this connector. So if we do have a problem with the MAF sensor, very, very likely it would be the sensor in that case, because we've got all of the components from our feed. Now, that is not good enough. We are going to have to measure signal from this MAF sensor while it is operating and see it measure changes. That is going to be a problem using this tool here, because I happen to know for a fact that this is a digital MAF sensor, and I've never probed one before. I've used a scan tool on it a few times, but I know, because I did the modifications here, this is a digital MAF sensor. So when I start the engine, if I probe that signal wire and the ground, when I turn this car on, that's going to change to 2.5 volts. And it's going to stay there no matter what I do, because of that on-off frequency that we are going to see, because it is digital. So let's go ahead and verify that. And okay, this thing just made a liar out of me. It is definitely reading much more than 2.5 volts. Let's see if it changes. Well, it changes slightly, but not proportionately. So, you know, there's only one explanation for this, and that is that there's probably, I would estimate, like a 90% duty cycle on this. Yeah, that is the only explanation of what that is. Okay, so you guys that are electrical engineers are either know that I'm wrong on that, which I know I am not, or you're saying, wow, you've come a long way in your electrical understanding, Matt. Yeah, I promised you guys that I would dedicate more time to this. Other guys are asking, what the hell are you talking about? And then other guys are like, damn, dude, when are you going to change a MAF? But let's take a break real quick, because this is important. I want to explain why we saw that, because this almost looked like it was analog, and as I increased RPM, we saw a slight drop there with the voltage. That is not as exactly as it looks, and I'm going to show you why that is. Okay, sorry, we're just going to go over this real quick here, but there is only one explanation for that, because I am not wrong. When I drew that square wave earlier, it is important to notice that this distance of time, remember we're talking about time here, this distance of time here is equal in my drawing to this distance of time here. So this amount of time on is equal to this amount of time off. And incidentally, just because this is at the bottom of the scale, that does not mean that it is off. It is possible in some systems, depending on the control and the polarity, that this is off and this is on. But the point is that this amount of time, if up here at 5 volts is on, this ratio of time that it is on compared to the ratio of time it is off is known as the duty cycle. And that is the percent of time on compared to the entire signal, the entire cycle for that signal. Now, you also are well familiar, I'm sure, especially because fuel injectors use this all the time, of the idea of pulse width. And most of you guys are aware that pulse width is the amount of time that the signal is on. And at a longer pulse width, there's more fuel added because the injector is open longer. You need to reduce fuel, you reduce the pulse width. So while a duty cycle is a percent for the time on relative to the whole cycle, a pulse width is the specific amount of time in seconds, usually milliseconds in an automotive application, is that signal is on. So it is not a percentage, it is the actual amount of time on. Okay, so just to make it real simple, let's make this extremely simple. Let's say that here to here is only 1 second. We're on half the time, we're off half the time. 50% duty cycle, 0.5 second pulse width. So hopefully that should be clear. Now, you do not always have a 50% duty cycle. The only explanation for reading 4 volts like that on that car, which I know for a fact is a digital signal, is this. The signal in this car has to have approximately an 80% duty cycle. So it spends, while it's still a square wave and it's still the same repeating signal over and over again, it's spending 80% of its time on instead of 50%. So now, again, with the voltmeter taking averages, it's more likely to make a measurement of the on signal than the off signal. So it is reflected, because when it's averaging, it is averaging 0.4 volts now, because we have an 80% duty cycle here. If this were a 50% duty cycle, it would have measured 2.5 volts. Now, admittedly, when I increased the frequency, we had this number drop a little bit, but the drop was nowhere near the proportion of the throttle angle. And so therefore maybe there was a little bit of change in the duty cycle, but the point is that it was not proportionate, it was not accurate. Now, that said, there was still a change when I increase. Does it indicate that at least there is some change in frequency? And it most certainly does. But the thing is that it's not a very accurate way of doing it. Now, granted, this is all conjecture here, although I'm positive this is what it is. The only way that I would be able to prove that this is indeed what's happening is if I had an oscilloscope, which, as you guys know, I don't have. Wait a minute, yes I do. Okay guys, for those of you that are following the channel, I know, but a lot of you guys have asked me, please do a video on MAF sensor diagnosis. And the reason that I never have done one up until now is because I knew I would have to cover digital MAFs, and I did not have the ability to do it properly and thoroughly and accurately unless I got a scope. As you can see, I finally got a scope. And no, I am surprised as well. It is not a picoscope, but I will do another video where I talk a little bit more about the scope that I got and everything. I actually just got it yesterday. I bought it used from a guy, and I have a complete kit with low amp probe, transducers, everything. I'll talk a little bit more about that. I will tell you, you guys were right. Totally worth the investment. But let's get back to work here. Basically, for those of you that are not familiar, don't be intimidated here. Scope is just a very, very fast multimeter. We're talking 2,000, 3,000 cycles per second on these frequencies, no problem. This thing measures like millions of times per second. So very, very, very fast. Anyway, like I said, we'll talk more about the scope and some of the applications later. What I want to do, and this one's a little fancy, I can actually choose my vehicle, and this model of the scope has a ton of information that the guy told me will actually tell me what the sensor connections are and everything. I, first of all, will not be using that here because I want to show how we can figure it out, since most of you guys will not have that information. And second of all, to be honest with you, did we not, because of our understanding and knowledge, figure out the connector pattern in like what, 5 seconds? It would be faster than if I were to scroll through all the vehicles and the whatever. I'm sure it would. Anyway, you'll have to excuse me, I'm not very familiar with this because I literally got this just last night. Let's go to the lab scope. I don't think we need 2 channels here. And let me start the car up and see if I can figure out how to get a signal on here. I actually have not tried this. I know what a lab scope is. I know what I want to do. The first thing is, I think 10 volts should work there. And 100 milli, that should work. I think that should work. So we should see the square wave on here. And let's go ahead and see what it looks like. Okay, so let's bring that up a little more. Let's see if I can figure out how to do this. Let's take a closer look there. There we go. You'll have to excuse me. I know some of you guys are like, dude, you're doing it wrong, but I promise you the next time I do a video on this, I'll be much more trained on this. The thing does come with an amazing amount of training stuff right on the tool, so I will do my homework, don't worry. But we can see that it is exactly as I said. The pulse width is quite long on here, and you can actually do things to measure the actual pulse width in milliseconds there. But we can see that we have clearly an 80 or 90% duty cycle at least. It is why, notice we've got voltage shown up here. Let me go ahead and do this. Okay, so here we can see we've got our traditional meter along with our scope signal. Notice that there is also a traditional meter shown in this smaller screen up here that's matching pretty much. Now, when I increase the throttle, watch what happens. This is going to squeeze together an awful lot, I imagine, representing that increase in frequency. But it is not going to be proportionate to the meter change. So let's try it. As you can see, the frequency did change, but it's not proportionate to the voltage change there. So there is a pretty good method there to test that we are getting proportionate frequency change. All right, and there's all kinds of goodies I can do with that, but let's go on to something else. And just because we saw the change in frequency and all that and it looked proportionate, it doesn't mean that there isn't a problem with the MAF sensor. The MAF sensor may not be calibrated right. So while it does have changes in the frequency, the MAF sensor is still not properly measuring the amount of air we'll talk about in the diagnosis part. Now, let's go over to another car real quick. All right, this is a MAF connector on another car. The first thing you'll notice is this badass wannabe has 5 wires. It looks like 1, 2, 3, 4, 5 wires. So based on our understanding, without having to pull up a wiring diagram or, God forbid, go on to a freaking chat room or forum or something, based on what we know, what design do we have here? We know that we have a MAF and IAT integrated together in this unit. So this presents a little bit of a problem, because if we watch the IAT video, we know that it also has a 5-volt reference. So how are we going to differentiate between which is which? Well, one way I could use my fancy tool, and I'm sure it would probably tell me. The second way, of course, look up wiring diagram, whatever. Or the third way, we can use our brain and figure it out based on what we know. So because of our high degree of understanding from all of our dedicated study, we have a lot of ways that we could actually do that using our brain. One way, we could remove this unit, put a hair dryer to it, and then test for which of the wires gives us a change in resistance. I actually show that in the IAT video, which is in the description. That would be a way of doing it. Another way we could do it is, we know that the intake air is going to be relatively constant, but the change in the MAF signal, and I don't know if this is digital or analog, I'm sure it's digital, we could do a test there to see if we back probe a couple of wires that we suspect are the MAF signaling ground, does it change when we hit throttle, while the other set of wires does not change, indicating we found which one is IAT, which one is MAF. All kinds of ways we could do it. So let's do this. One of the things, because it's 5 wires, we already know the design. We know there's going to be 2 wires for the IAT and 3 for the MAF. Okay, so let's just go ahead and get a reading here. And again, I have no idea what these wires are, but we're going to figure it out. One thing I think I may see here is possibly a black wire. So obviously I'm going to suspect that to be ground. I don't know for sure. And when I probe that, we get very low voltage right there. Actually kind of suspiciously low. That actually, I am going to take an educated guess and say that that is the MAF sensor signaling ground. Now, given that information, let's assume that to be true. If that is correct, and I am on the MAF sensor signaling ground, what type of sensor is this? Is this digital or is it analog? Almost certainly this would be an analog, because we're close to starting at 0 and we would increase with the engine speed. I find it very hard to believe, this is like a 2013 or something. I find it very hard to believe that that would be the case, but we'll have to see. If this is the MAF signal, we know the circuit design right off the bat, just from that voltage reading. Either that, or when we start the car, it's going to have like a 10% duty cycle or something, which isn't going to happen. But let's keep that in mind. Let's see what happens. Now let's move over. I'm confident that this black wire here is also a ground, most likely for the IAT. Let me check that. And we've got 2.6 volts. Now, remember, the engine is not running. The engine is not running right now. I'm much more inclined to believe that is the IAT. If the engine were running, I would say that we probably have a digital MAF. So let's do this. Let's go ahead and turn the engine on. And let me make sure these wires are out of the way of the belt, and see what happens with that number and what happens if we change over to the other side. Actually, you know what, better yet, let's just go ahead and leave that there, put the scope on the other side, and we can kill two birds with one stone. But of course, you could do the same thing sequentially with just the meter. The volt, that's probably going to be small to see here, so let's go up here and use the digital multimeter. It's got this big ass meter on it that I think is kind of cool. There, if you can't see that, you got a problem. And what we're going to do is, you know what, actually here's the thing. Let me get back into that ground there. There's one wire that we forgot to test here, and that is this green and yellow right in the center. What do you want to bet that that's going to be the 12 volt power source for the hot wire? So let's go ahead and do that. Might be a little helpful. Okay, and when I do that, it, well, it clearly means that it's out of range. Because we're only on a 1 volt scale. So we can change that. 20 volts should do it. Okay, so there's our battery voltage, obviously. So that's really cool. You see how intuitive this tool is, by the way. I love it. What we want to do now is I want to get off of that because we know that that 12 volts is going to be constant. So let me get off of that. But this makes kind of engineering sense, sort of, that the left side is probably going to be the MAF sensor just from the order of the wiring. So let me get back into what I believe is going to be the MAF signal. Okay, there we go. And let's get back out of here. I got to tell you, I don't know for sure, but I'm pretty confident we've got this right. And this is going to be an analog measurement. Let's go here, back to our, I wonder if there's a quicker way I can do that. You guys don't have to worry about making comments to help me out with this. I'll figure it out. But if this is analog, let me increase this here. If this is analog, we'll know it. If this is digital, we'll certainly see the square wave. So let's go ahead. By the way, I hope you guys follow what I'm doing here. I'm hoping I'm not losing you here. But what I'm doing is I'm trying to find out for two things kind of simultaneously. First of all, which of the wires is for the MAF, which is for the IAT. I'm not interested in the IAT. And second of all, we don't know the design, whether this is digital or analog, if we do find the MAF. If this number doesn't change much, but we see a lot of change here with throttle, then we know that we are connected up to the MAF here and the IAT here. Let's find out. All right, it is pretty obvious that is going to be an IAT and that is going to be a MAF sensor. So the one way, let's go ahead and increase the RPM. Unfortunately, and you know what? There's no square wave here, and we're at 2 volts. There is no question about it. This is going to be an analog signal, which means I'm going to have to dramatically change my time frame here. Let's put it on to maybe a couple seconds, like that. Okay, so what's going to happen, this is going to look, because there's no square wave, obviously this is analog. I'm amazed by that. And we're going to see when I step on the throttle, the IAT, of course, not going to change much, but that's going to look almost like a throttle position sensor signal. This is a drive-by-wire vehicle, so I'm going to have to go into the vehicle to do this, so you'll get to see it before I do. And actually, because of that, because you're going to see it before I do, I'm going to increase the time frame so I can come back and see it. Okay, quite obviously, and we can bring our scale a little better here. Okay, quite obviously, we are on the MAF sensor. I'm no longer worried about this. I'm just going to go ahead and get rid of it. That was clearly on the, that was a pretty good guess, I guess. But let's go ahead and verify if I go wide open throttle, that voltage should spike up pretty close to 5. And you can see it's giving a min-max here, it looks like. I'm sure that is. All right, the engine has a rev limiter on it at a certain number, so it only limits me, but clearly we are, I'm not quite sure why it stopped there. Let's try refreshing it. But clearly we are on a MAF sensor. So we could measure this. We don't need the scope. Let's get rid of the scope because I know most of you guys don't have it. Let's go ahead and hook our DVOM up to it. Actually, I take that back. We do have a DVOM here. So this would be no different than hooking up your standard DVOM, and we're going to be able to see the changes in voltage proportionate with the throttle engine speed bringing air into the MAF sensor. All right, and again, activated the rev limiter there. And clearly you would have seen the difference there. I didn't get to see it, but I'm sure it happened. Okay, you know what I'm going to do just to prove a point of principle here? Let's go ahead and use our cheat sheet here to go ahead and pull up that wiring pin just to make sure we were right, but also to see if we can get a speed comparison, whether brains can beat a computer. I'm going to go to US imports. This is a Subaru. And I'm sure it's going to be under fuel injection. Boy, I would expect a lot more stuff there. One of the things getting this tool used, it's only going to go up to 2007. So let's go ahead and do that. This is an Outback. This is a 2.5 liter Outback. Okay, yes to accept. And sorry if this is boring, but okay, so now we got to find the MAP. I'm sorry, the MAF sensor. Okay, it's got to be called something other than the MAF sensor then from Subaru. So let's see, we've got an air fuel is not it. Barrow, that's going to be a MAP. Is there also a MAP on here? No, so Barrow is going to be the MAP. You know what? Oh, there's the IAT. I guess we could have looked at that. I do not see anything that even remotely, there is no MAF sensor on here. You know what? That is cool. And I will tell you why that is cool. It is because you can imagine that your 98%er that just figures, hey, I don't have to learn any of this stuff. All I need me is one of them fancy gizmos and it just tells me what to do and I don't even have to understand what I'm doing. Well, guess what? It didn't have the information you needed there. What are you going to do if you are a mobile mechanic and you are in the field doing a diagnosis and your super fancy tool didn't have that information? You're going to ask the customer, hey, you don't happen to know how to probe a MAF sensor, do you? You're stuck like Chuck, man. So you still, even with really good equipment, have to understand what you're doing in this stuff so that you can figure your way out of situations. That I am actually thrilled that happened. And as you can see, even if we did have the ability to find the MAF sensor in there, because of our understanding that we've spent time learning for the last hour, we would have been able to characterize that system with our digital volt ohm meter faster than we would have done with this anyway. So that feature with the components and everything, not really so much a selling feature for me, but anyway, enough with this. We're going to use this again when we get into the diagnosis, I bet. So let's get back to the dry erase board of knowledge, clean up this section, and then the next section, of course, will be diagnosis of things that can fail in a MAF sensor and how to diagnose it. So to close out this first section, we still have two more things that we have to do for understanding the data outputs based on what we've learned earlier. We still want to look and see if you happen to own a frequency meter, like a higher end DVOM that has that. We need to look at what that looks like on a digital MAF sensor. And then finally, let's go ahead and look at if you have a scan tool, what your scan tool output data would look like and make sure it matches what I said earlier. Since I don't have a DVOM that has frequency measurement, I know I saw this in here when I was playing with this last night. So again, I'm just hooked up again between that signal wire and the ground wire. If you have to ask, hey, you didn't show what color wires you're probing, the color of the wires is insignificant. We are not looking at these as black, yellow, green, gray, whatever wires. We are looking at these wires by function. By what is the ground, what is the signal, what is the power. If you are still at the point after watching this video that you need to see the colors of the wires and you're still thinking in that way, I don't know what to tell you, you got a ways to go. But anyway, let's see here. And it's not there, and I apologize. There's frequency right there. Okay, let me go ahead, and I have no idea what we're looking to do here. Let me go ahead and start the car, and obviously we're going to have to set some scales. This is completely new to me. The one thing I know, let's see, we want, we're surely going to, I mean, 10 hertz, we're going to be way above that. Yeah, let's do that, and then, because there's already actually should be a frequency. I think I have the car on. I forgot. Let's go ahead and run this and see what happens. Okay, I am totally figuring this out as I go, but looks like a pretty good guess. We can see 2.33 kilohertz there, and it looks like I've got maybe 2 channels going or something here, but let's see. And it goes up to 4.5 kilohertz almost. So we definitely can see a frequency change by using the frequency meter. We can maybe make that a little more, I think we can probably go here. I don't know that that graph helps very much, but we can, now you can see it is kilohertz. And one of the things that's pretty cool is a lot of times there'll be a specification in a service manual for your kilohertz. Mine's a little bit high actually, but again, I believe that's because of the modifications obviously for the engine. But we should see what obviously is a very proportionate signal increase, a more compression it would be of that square wave represented just from the kilohertz signal. All right, and our final part of this initial segment is looking at the scan tool PIDs that you would get. So we already have an idea based on the function of the MAF sensor what we might expect. This is on the Trans Am, so I don't expect we'll see voltage on here. But let's see what we've got for it here. And while I look, we'll zoom in a little bit there. If you told me a year ago I'd be doing a kilohertz measurement on a digital MAF sensor, I would told you you were crazy because I wouldn't even know what you were talking about. So obviously anybody can learn to do this if you just dedicate yourself to it. There's mass flow air rate. So we've got 3 things here for mass airflow that are available. Let's go ahead and pick those. I'm not quite sure what mass airflow sensor 1 is. The rate is guaranteed. That's going to be on this car in pounds per minute. The frequency it's going to show, as we saw before. I'm not sure what this third one is though. Okay, and the third one is apparently pretty much some type of extrapolation off the first one. That may be with and without IAT, possibly. I really don't know. Notice our hertz is pretty much what we found using the hertz meter. So if you did not own a hertz meter, scan tool would work, and vice versa. And that's pretty much all the data we have. Increases proportionally with the hertz. There's the data from the scan tool, just like I said you'd find. All right, those of course were the PIDs that we got from a digital MAF. Let's go ahead and look at this analog MAF that we know we have on this other car. I expect we'll see voltage. So let's see, let's clear this out. And there it is, mass. Well, all it has is mass airflow rate. What kind of a jip is that? Only 1 PID there. Well, you know what? All the more reason why you want to have a good understanding of this stuff so that you can have multiple approaches to a diagnosis. All that's going to do is just give you the same reading in grams per second there. So, all right, disappointing. All it does is give the mass airflow rate, no voltage reading there or anything. So that was kind of useless. All right, well, that just goes to show that you are a lot better off having a lot of knowledge and understanding than just relying on the scan tool or whatever. That was an amazingly minimal amount of data from either car, actually, if you think about it. But anyway, for this first part of this diagnosis and understanding video, we have achieved our goals, I hope, of understanding the purpose of the MAF sensor and also the different types of MAF sensors, the different types of circuit designs that are available with MAF sensors, lots of ways to be able to assess that circuit design, read the output using various methods. I think we covered a lot here. So it's time to move on to part 2, and that is taking that information now and learning how to make a diagnosis on a failed MAF sensor and also using the MAF sensor in diagnoses of other sensors. So we will go ahead and we will do that on the next video, but I will give you a preview here. And in the next video, we will cover the 4 possibilities you would have and how to test them for a MAF sensor problem. Those would of course be a failure of the MAF itself, some type of lack of integrity with your circuitry, a inaccurate MAF, very common one, dirty MAF sensor, things like that. The MAF being inaccurate will often not give a MAF code. These would give MAF codes, and your average 98% idiot is going to change the MAF sensor, probably get lucky on it. But how many people change the MAF because of lean conditions, things like that? That is the result here. And the other one is the MAF on a referenced code. We actually saw that in my last series with the Volkswagen, didn't we? So this is, of course, referenced is a term that I personally use for when a part is actually given a code in the computer for the check engine light, but it is erroneous. It is miscoded by the PCM because of lack of communication with other sensors, which brings us back to the first thing I said in this video. We have to understand everything. But of course, we'll get more into that into the next video with the diagnosis of problems. And as far as for this one, thanks for watching. I hope you found this helpful. We'll see you again soon.